Good day, everyone, and welcome to our Che211.1 class. Today, we'll be looking at the process flow diagrams. We've already covered chemical processes, so I'm not going to, I'll just move to where we stopped the last time. So let's look at process diagrams. What are process diagrams? In general, chemical processes are complex, just like what we've been saying all along. So there is need, therefore, to present such information in a manner that is least likely to be misinterpreted. So that you don't need to be at the plant to be able to visualize what is going on within the plant. And the most effective way of communicating this information is through the use of flow diagrams. As a chemical engineer, it is essential that you should be able to formulate appropriate process diagram and have the skill to analyze and interpret such diagrams. So we'll be looking at three different diagrams: block flow, process flow, and piping and instrumentation diagrams. The process flow diagram, PFD, is the most useful to chemical engineers, especially when you are practicing. But the building block to all of them is the block flow diagram. So we'll start with that. And the block flow diagram can take one of two forms: the block flow process diagram, which is drawn for a single process, or the block flow plant diagram. Notice the word here, it has a basic difference. The other one is process, the other one is plant, which is drawn for a complete chemical complex involving many different processes. Both types of the flow diagrams are useful for explaining the overall operation of chemical plants. So let's look at the block flow process diagram. What is done in this case is that each unit operation is represented by a block or a square or a rectangle. And each of these blocks in the diagram represents what process is taking place within that block. And it may consist of several pieces of equipment. Just doesn't mean that it's just going to be one. It will be quite a number of equipments that are lumped together. So basically what such diagram does is to give you a feel of what the process is. For instance, I can draw a block like this and put inside a block, and just write I can put something like this and just say that, well, I put heating in the block. And what is it telling me? It's just telling me that I'm going to raise the temperature of whatever feed that is coming in. and whatever, raise the temperature before it goes out. So I can have that kind of log flow. It's just saying that we're heating. And what does the heating, how will you raise the temperature? May actually involve two different stages, in which you first of all have a heat exchanger there, for example, that will raise the temperature first, or you can have a small separator first before you start raising, or you start putting the heat exchangers. It can also be a series of heat exchangers. It will not just be one heat exchanger. So depending on what your initial temperature is and what the final temperature is. So it just shows the main features without getting bogged down with the details of what is there. So as you will expect, there are standards, which is called conventions, for drawing your flow diagram. Usually operations are shown by blocks, or just like I said, just means rectangle. Each of the operation is shown by rectangle. That's why they normally call it a block diagram or a square. The major flow lines are shown with arrows giving the direction of flow. You look at that last example that I gave, you could see that I was putting in arrows, and that tells you what is coming into the block and what is leaving the block. And generally speaking, the flow flows from left to right. Normally too, if there are light streams, it's usually done up, with the arrow facing up. If you have heavy streams like liquids and solid, the arrow is usually bottom. And what do you also do on that block diagram? You also provide some critical information. For instance, you may need to specify the flow rate, for instance, the temperature, and if there is need for it, you may also state the concentration or the pressure. And if line crosses, then the horizontal line is continuous and the vertical line is broken. And what do we mean by that? Let me just see if I can illustrate that. If you have a flow that has to go like this, that is going like that. That's the flow. And then another one needs to cross it. This is usually not allowed. What you're supposed to do, this is not right. You need to sorry. What you need to do is that you need to have that horizontal one, which is like that. And then the one that passes through will be something like this. Sorry. It'll be something like this. Just to show us that well, there are two streams. This is the one that is going horizontally and the other one is crossing over it. Of course, this will have to be straight lines. And lastly, there is a simplify, just like I've said earlier on. You will also need to include the flows, and in as much as possible, your flows will have to balance. We'll get down to that one, especially in the next semester, when you will be handling Che211. So this is a typical example of a block flow diagram. You can see here, this is for the production of ammonia. And we are producing ammonia liquid. And where are we producing the ammonia from? We are producing ammonia from nitrogen and hydrogen. And of course, you can see that there are some values that are in cycle here. That is telling us the streams. You may be wondering, what is the difference between 1 and 2? Well, what I would like you to do is to tell me the reason why you have 1 and 2. Why do you have 1 and 2? Why do you have 1 and 2 in this diagram? So please, that will be your first question. Why did you name them stream 1 and stream 2 in this slide? So you answer that one. Why is it named differently? Or put in another way, what do you think stream 2 is when you look at this diagram? What's the relationship between stream 2 and stream 1? You can also tell, that's another way of telling me whether they're the same, and if they're not the same, what is the relationship between the two streams? So we have that coming into the system, and then it goes into a reactor. And you can see that we've already given some specifications here. We've given the temperature within the reactor. We're also given the pressure within the reactor. We'll say that the pressure is 300 bar. So again, if the pressure is 300 bar, what is its value? In SI units. That's the second question that you need to answer. At the end of the day, we'll be able to tell. When you check the Canvas platform, you will see the link for providing your answers to these questions, this quiz. So you can see in the reactor, that's where the reaction takes place. And when the reaction is completed, you then have your products. And of course, you are not going to have 100% completion. So from there, it goes through a boiler. If you look at this, this is a temperature, this is a very high temperature, 450 degrees C. So which means that the product coming out from here will be at high temperature, so you don't need a boiler. And what would the boiler do? The boiler is just to generate high pressure steam. So you put in water in the ordinary water, and then the boiler, it exchanges heat from what is coming from here, and then release steam at high pressure. Because remember, it's also coming in, the pressure won't be at atmospheric, so it's going to be a little bit high when it's still coming out from the reactor. And from the boiler, what do we need to do? We need to separate our product, which is what we need, the ammonia from the nitrogen and the hydrogen. So it goes into a chiller where the ammonia is converted to, is liquefied. Then you have your liquid ammonia going out. And you can also see the process conditions here. And what you have separated is then sent back. So you can see from this simple example, it just gives us the overview, gives us a feel. But it didn't specify what type of reactor you're going to use, what type of boiler you're going to use, what type of chiller you're going to use. It didn't give all those details, but at least you have an idea now of what should happen here. So the process flow diagram often forms the starting point for developing the process flow diagram, which is what we'll handle in a minute. So the block flow plant diagram is also similar to what we have done. Remember the other one, just block flow diagram. You can also do the same thing for the whole plant, the whole process plant. And in this case, each block in the diagram represents a complete process in itself, including all the, and because you are having other equipment, there are also standards for or conventions for representing those other equipment. For example, compressors, turbines are shown as trapezoids. I hope we all still remember our elementary geometry, what a trapezoid is. Just something like this. It's a little bit slanting rather than square. So for the plant, it gives us a complete picture of what the plant does and how all the different processes interact. Just like I said, the convention is also similar to what happens with the block flow diagram, the one that we considered earlier on. So you can see here an example of a block flow plant diagram for converting coal to higher alcohol fuel process. Don't get confused here. These are some of the things you are going to be doing later on in the program when you get to your higher level. So you can see each of the main process are represented by blocks. Then the compressors and the other equipments are represented by the trapezoid, compressors, turbines. And you can see each of those ones here. And your stream numbers are also stated. You can see the compressor that is there, which is the air coming in is compressed. And if you look at this side here, in a nutshell, you'll be able to see all the products that are coming from the system, from the plant, that you're obtaining from the plant. And when you look at this end here, you can identify all the inputs. So what I want you to do for me, which will be your next assignment, is to look at this plant and tell me how many input streams do we have? And how many output streams? So you look at this and then tell me how many output streams and then how many input streams. Remember, the input is just indicated by the arrow, just like you can see here. These are typical inputs here. This is another typical input. So you look at this. I don't want you to tell me the name, just tell me. Tell me what the number of inputs, just count the number of inputs and then the number of outputs in this particular plant, a block flow plant diagram. To take a close look too, you also see in these cycles or ellipse, you can see the stream numbers. They are all there. So now let's look at the process flow diagram. We've looked at the block flow diagram. So let's now look at the process flow diagram. As we mentioned, the block flow diagram is the starting point. You just put everything in boxes, and then that gives you an overview. The process flow diagrams move a step further than that. It gives us the bulk of the chemical engineering data that is required for the design of that plant, of that chemical process plant. And when you look at a typical practical PFD, it will have the following: the major pieces of equipment in the process represented with each piece being assigned a unique equipment number and a descriptive name. The process streams are all shown and identified by unique numbers. Those streams are there, and then the data will either be displayed if there are not too many. If there are too many, then it will be included in an accompanying process summary table. If there are many, that's what will happen, so that the diagram doesn't look too crowded. Just like what we had in the last diagram for the block flow diagram. And the other thing which is also shown in a typical PFD is the utility stream. And what are these utility streams? What are these utility streams? These are the streams, these are the streams that, what are the utilities? The utilities basically include things like steam, instrument air, because for instance, you need to maintain some of the valves, some of the control valves. Don't worry if you don't understand what it means. But I'm sure by the time you go on in the program, it will become clearer. But for now, have it at the back of your mind that you need air, compressed air, you need steam, which are all used within the plant, not just in one place, at one point. It will be used in other areas, not just one area. You also have things like fire hydrants, which are points where you need to have water in case there is fire, for instance, and you can easily, the firefighters can easily have access to. There are also the waste streams. So these are all part of the auxiliary requirements for a typical process flow diagram. I mean, for a typical process plant. So now let's take a closer look at the PFD. Usually you can categorize it into three different areas. The process topography, I mean topology, which more or less gives you just a pictorial view with minimal information. And then the stream information, which is what we said earlier on. In some cases, you can put it on the process topology. But in some other cases, when the informations are quite many, it's good to put it in another tabular information, tabular form. And then each of the equipment too, you also need to provide that. Let's take a look at each of this. The topology more or less is just the location of an interaction between the equipment and the process streams. And each equipment is represented by icons that identify specific unit operations. And then the list of equipment numbers along with a brief descriptive name of the equipment. And when a piece of equipment wears out or is replaced by a new unit that provides essentially the same process function as the old, then the new piece of equipment will still retain the old equipment name. For example, if it's a heat exchanger 101 and it's replaced, then you can still keep the name as 101, H101, or they can just change it to 101A. If, on the other hand, there is a significant process modification, then the new equipment will be given a new name and a new number. So this is a typical example of a process flow diagram. And this is just for the production of benzene through hydrodealkylation of toluene. So that's the process. You can see the inputs coming in, and you can see the summary of the various equipments on top. It's a little bit, it may not be very clear, but that's what is on top. That's the summary of the equipment. And you can see the various equipment that are here. And you can see their names. So you see that we have used some symbols. Some symbols have been used here: V, H, R, E. What else? And that is all. So you can see all that here. What do they mean? We'll see them. Remember, we said that a process flow diagram should not be ambiguous. It should be easy for you to read it and interpret. So we'll look at the conventions for naming them. So you can see these are some of the ways of representing different vessels, different equipment. You have heat exchangers, which is what you have here. You have the columns or towers where separation takes place. You have reactors where reactions take place. And you also have, these are heat exchangers here. This is a fired heater, which is different from the heat exchangers. Because here, in this case, yes, both of them exchanges heat. But here, usually there are streams. Then you have storage tanks where you store your information. Oops. Oops. Sorry, I think I have, yes, let me go back. So these are the standard symbols. Let me share my screen again. I've gone off the screen sharing. Go back to where I stopped from. So we have the storage tanks that are here. These are the storage tanks. You have the pumps. You have reactors here. You have vessels here. And again, generally speaking, the process input is represented by this. Valves are represented by this. And then stream numbers are usually put the instrument flag, the control valve. You will notice the difference between the valve and the control valve. The control valve has this controller and it's represented here. This is just typical examples, typical symbols that are used. It's not exhaustive. There are quite a number of other symbols that are used. So now let's look at it, because in the other one you've seen that we saw H, V, and all the rest. So if I go back, I told you that we'll get to, you can see them here. H101, P101A and B. So what does this mean? So we can see them here. When you see P there, for instance, what it's telling you is that it represents a pump. And the general format is that you see it as this. You will see it will be represented as this, where your XX identifies is a letter for the equipment classification, which can be C, E, and so on and so forth. And that was why in the other you saw something like H, I think 101, something like this. So if you look at this the way it is, what this is telling, your XX is this H, your Y is this 100 in this case, and your ZZ is 01. In this case, A and B is missing. So your XX designates the equipment. Your Y designates the area within the plant where that equipment is located. And the ZZ is the number that is used to identify that equipment within that area. So what this is telling us is that if you see H101, for instance, H101, this is telling us that, well, you have a heat exchanger because you have a fired heater rather. You have a fired heater that is located in area 100, and the number of that fired heater is 01. That is what it means. So I hope with this now you can go back to that flow diagram, the PFD that was shown earlier on, and then be able to identify the various equipment that is there, and also tell us the area where it is located and the equipment number. The last thing that is here is this is this A stroke B? Usually this is used to identify parallel units. That means that these are two units that are there, and at any point in time, one will be in use and then the other one will not be in use. And this is usually done when you have a critical equipment that is you can't afford to have a downtime. That means you can't afford not to have that particular equipment operating. If it's not operating, then there will be a big problem. You need to shut down the whole process plant. So in such a case, you need to have a backup for it. But what you then do is that it's only one that is shown. The second one is not shown on the PFD. The A and B designates that there is an alternative one that is available. So I've explained those ones to you. What we have in this slide is just what has been explained. If you have P101 A stroke B, the P there is indicating that it is a pump. The 1 is indicating that that pump is located in area 100, and 01 is indicating that the specific pump number is 01 in unit 100. And A and B means that there are 2 pumps installed. 2 identical pumps are installed, but at any point in time, one will be operational while the other one will be idle. Again, just like we said, each stream will be identified by a number, always put in the diamond box. If you look at that last table, if you look at this table here, you can see the stream number. It's usually in that diamond shape. That's what is done with the process flow diagram. Put the stream number in this. So those numbers are there, and then your stream information, you will then be able to give the summary for each of them. We've also mentioned earlier on too that utility streams are also indicated there. And these are services that are required at the plant to service the plant, to service the different segments of the plant itself. And they include electricity, compressed air, cooling water, refrigerated water, steam, condensate, return, inert gas, and so on and so forth. So you can see again here the conventions for providing the stream information. For the process streams, we've already seen that one earlier on. The conventions shown in the previous table, diamond symbol for locating for the flow lines, in the flow lines for the stream, numerical identification number inserted within the diamond, and of course, the direction shown by the arrows. For the utility streams, you see some of these small numbers that are there, just to tell us what it is. If you see LPS, for instance, is telling you that it's a low pressure stream. And then Usually, what do we mean by low pressure steam? It means it's between 3 to 5 bar G. And what does bar G means? What does bar G means? Bar G just means bar G means bar gauge. So the assignment I'm going to give to you too is to tell me what is the relationship between bar and bar G. So that's the next assignment that you need to tell me. You need to tell me what the relationship is. So read that one up and then you should be able to answer that question. So the stream information, just like we said, if it's small diagrams containing only a few operations, you can include such stream information directly on the PFD. But for complex situation, only the numbers is provided on the PFD, and then the stream information is normally given in a flow summary table. So let's look at what it looks like, a typical example of what it looks like for the previous one. Well, before we do that, this is just telling us the typical information that is provided in the flow summary. Stream number, temperature. Remember that we have put the bar here as a unit of pressure. In most process industries, they still use they mix the units. Some still use the FPS unit, some use the SI unit. So these are typical information that will be provided in the flow summary. And you can see a typical example here for the benzene process flow diagram. You can see what is in stream 1 and so on and so forth. You see the temperature there for stream 1, for stream 2, and so on and so forth. So let's do a simple example, even looking at the same slide, that benzene. The conversion of toluene. So, and what we're saying here is that determine the conversion per pass of toluene to benzene in R101. From what we've done, we now know that R is a reactor located in unit 1 in area 100, and the number is reactor 01. So if we look at that, what do we then, the question is to ask, well, what's the conversion? Now we need to look at that stream first. Supposing we'd assume that the conversion X, which is the benzene produced in reactor, over the total, remember our definition before when we were saying the yield in the earlier lecture. So your conversion is going to be benzene produced in the reactor over the total toluene fed to the reactor. We then need to ask ourselves first here, which stream are the input streams to reactor 101? And what are the output streams? So if we take a look at this, you will see that this is one of the inputs, which is stream 6, and this is another input to the reactor, which is stream 7. And of course, in this case, what is the output? The output is the output from the reactor is this stream here, which is stream 9. As the output from the reactor. Because don't get confused with this. This stream does not enter into has nothing to do with the reactor itself. If you take your balance around the reactor, which is what we are interested in, you take your balance around the reactor, you will see immediately that, let me clear it so that you can see it. Take our balance around the reactor, and see clearly then that there are two inputs coming in, stream 6 and stream 7, and there is only one stream leaving the system, which is stream 9. So once we've been able to identify that, we'll then go to the stream, the flow summary table. And you can see from there that the total toluene that is coming into the reactor is the one from the stream 6, which is 144, plus the one coming from stream 7, which is 0.04. So if you add the two, then you'll get this. And where is the benzene that is produced? The benzene that is produced is in stream 9. The benzene that is produced is in stream 9, which is what is leaving the system. And then which ones are coming into the system? This is as 116. But if you look at stream 6, if you look at that summary table, you will also see in that summary table that there is a little bit of benzene that is there. So we need to subtract that, that's 7.6. I said so a little bit of benzene in stream 7. So then in stream 7, so we also subtract that from it. And on that basis, we can now see how much is leaving the system. And since we've been able to calculate what is leaving the system, the benzene that is leaving the reactor, our X will just be this amount here divided by what has come. And that will be the conversion, which will be 0.75. So you have the conversion here, and from what we have here, my next question will be, what is the unit of X? What is the unit of X? So the final aspect of the PFD is the equipment summary. Again, just like we have for stream summary, you also provide the necessary information of the equipment that you can now use on the equipment that you can use to estimate its costs, and then use informing the basis for the detailed design of the equipment. So we can see some of them here. This is more or less like the information that is made available in the equipment. If it's a tower, for instance, that means if it's a column, then you need to provide the size, the pressure, and the temperature. If it's a tray type, then the number of trays, the height and type of packing, and so on and so forth. I'm sure by the time you get to your year 4, most of this will then become fairly easy for you to understand, because you have taken courses that will enable you to use such information effectively to design the different equipment. So it's the same thing that goes for heat exchanger, tanks and vessels, and so on and so forth. Again, for that, a simple example, you can see the various equipments that are there. E is supposed to be the exchanger, and then the type will be there, and so on and so forth. It's just for you to have a feel, just like I said, just to have a feel of the kind of information that you will see there. Some of this now you may not be able to understand the full details because this is just an introductory course. I can also see in this last slide here because I'm sure some of you will have been asking, what does those FH, FLH, and so on and so forth, what does it really represent? So you can see the key to all the symbols will also be specified in the summary table, equipment summary table. So here you can now see our PFD diagram in which all the informations are put in place. Yes, you can do this because this is a fairly small process unit. So you can put everything on the same page. But if it's a bigger one, just like we said, you need to put them in separate. You need to put the stream summary in a separate table, the equipment summary in a separate table. The last one is a piping and instrumentation diagram. And usually here, this is more or less like now we're now moving to the last stage when you're looking at a process plant. At this point in time, you've already done your design and the equipment is, the process plant is almost good to go. So the P&ID diagram, which is also known as a mechanical flow diagram, provide information needed by engineers to now begin planning for the construction of the plant. And that's why I said you've already finished your design. Now you're at the stage of now saying, well, look, we want to go from the drawing board to the field. So you now need to give the details, which will include operating condition, stream flows, equipment locations, which is what you have done under your PFD. Now from 4 down, that is where the subtle differences come. Now I need to indicate the piping, the pipe lengths, the fittings, and then support structures and foundations. So from what I said earlier on, your PID is going to be derived from the PFD. So each PFD may require many PIDs to provide all the necessary data. The utilities connections are also identified by number boxes in the PID, just like we have done. And because the PIDs can be very big at times, it may also include some circular flags on the diagram to indicate where information is obtained in the process and identify the measurements taken. One of the uses of the PID is also to train the operators, the people who will operate the plant. Because with that, you can now use it to trace the different equipments, the lines, the pipings. And before you even start operation, you can use the PID to understand what is within the plant. And physically, when you now go out, you can relate it to it. It's also very important for the development of the startup procedures when the plant is not under the process control systems. Just like we did for the other one, there are also conventions for constructing P&I diagrams. And these are some of the conventions that were put here on this slide. I'm not going to read it. I'm sure you would be able to read it on your own, at your own time. Some further details are here, but then you will notice that there are quite a number of similarities with the PFD and the PIDs. It's just that the PIDs are a little bit more detailed. And you can see the PI&I diagram just for a section of that benzene that we showed earlier on, just for the distillation section. You can see the extra details that have now been put into it. So you can see the distillation column here. You can see the ray boiler here. You can see the condenser at the top. But like I said, just have a feel of it. You will do all these things, the technical details will become obvious as you move to the higher courses. When you do separation processes, then you will be able to understand and appreciate these diagrams more. So here is the second exam exercise. This is one of the exercises that you need to submit. So again, this will be all the assignments in this particular up to this point will be done on individual basis. So this second exercise, it says during the retrofit, you can read that one up, and then after you read it up, answer those two questions. Finally, the exercise 3, this will be a group assignment, in which case you need to choose one chemical engineering equipment or vessel, and then download a video from the web showing how the equipment or the vessel works. After you've downloaded it, watch the video and summarize your understanding of the principle governing how it works. And in this case, once you've been able to choose, like I said, this is a group assignment. It's not the Piazza platform. Put it on the Canvas platform, please, for others to see. And of course, I will give you the link for you to submit this group assignments as well as the individual assignments. Remember that it's not Piazza platform, it's a Canvas platform. So what you should do is that the summary should just be a maximum of 1 page, your understanding. Your summary. So like I said, it's not a PSL platform. This is a Canvas platform. So I think